Thank you. Thank you. Very good afternoon. Thank you, Indu, and thank you, the organizers, for giving me this wonderful opportunity to talk to the young minds. So in the next 30 to 40 minutes, I will try to give an overview of what is space weather and how it impacts our planetary atmospheres. So when we talk about space weather, first let us try to understand what is weather. When we talk about our Earth's atmosphere, weather refers to the short-term changes in the atmosphere. We think of weather in terms of temperature, humidity, precipitation, and atmospheric pressure as in high and low pressure. So these are basically the state variables to understand our weather. So this weather, which we encounter daily or which we experience daily, happens in the troposphere, that is the part of the Earth's atmosphere which is very close to the ground. And this affects our daily lives. But what we are going to see in this lecture is not the weather of the lower atmosphere, but the weather of space. But now a natural question. The weather of space, why do we care? Because it's too far and too tenuous. Unlike troposphere, where we are having daily contacts. So why do we care? Because space weather can affect technologies. An example is that an unexpected space weather event caused the loss of 38 satellites by Starlink in February 2022. Apart from this, we have seen that space weather can affect the signals from navigation systems, that is like GPS, which can cause degraded accuracy in positioning, etc. And also energetic particles can penetrate satellite electronics and cause electronic failure during space weather events. So really, space weather is important to us and because it affects our technology. So what is the definition of space weather? Space weather includes any and all conditions, events on the sun, in the solar wind, in the near Earth space, and in our upper atmosphere that can affect our spaceborne and ground-based technological systems, and through these, our life and endeavors. So this was an early definition of space weather based on the near-Earth space environment. But as the humankind progressed, our presence has been increasing to other planets and planetary systems also, and naturally, because of that, the definition of space weather also expanded to include all natural space environments, not just the Earth's environment. So, what happens when a space weather event occurs? Actually, our sun, or the host star of the solar system, is not as happy as always, and it can really be extremely angry sometimes. And when it becomes angry, it can unleash very violent space weather, that is storms that can radiate enhanced extreme ultraviolet and X-ray radiation into space, and really giant clouds of magnetic plasma. The cloud size can be even bigger than that of Earth. This kind of giant cloud of magnetic plasma can propel into the Earth and other planets as the geometry may be. And then not only this cloud of plasma, it can also spray a lot of charged particles, energetic particles throughout the interplanetary space. And these energetic particles can affect our satellite electronics and so on and so forth. So this is what space weather is all about. Now, let us look into a brief history of space weather, how it all began. So this is a picture in 1580 of a town of Germany. The people then saw a very large and frightening sign in the sky after sunset. They were not knowing what it is, and they didn't even understand what it is. So naturally, they were frightened. And this text, which is shown here, actually continues in a religious manner. They are telling like this is some kind of a magic sign from the heavens and so on. So this is 1580. At that time itself, we had some experience of the impact of space weather on our planet. Now, people have started observing or studying the Earth's magnetism. In this area, Gilbert in 1600 correctly interpreted the deflection of a compass needle. Actually, compass was known to humanity even before this, and it was Gilbert who correctly interpreted that the deflection of a compass needle is due to the terrestrial magnetism, and he stated that Earth itself is a giant magnet. This then actually was an inadvertent step towards understanding space weather in a scientific way. So, not just the Earth's magnetism, people have been observing sun as well. For example, ancient Greeks and Chinese have observed sun with the naked eye, and they have seen that there are dark spots on the sun. The picture what you are seeing here is a full disk of the sun, picture made by Galileo using a small telescope on August 20, 1610, and he has made this picture of sunspots here. So, what are these dark spots seen in the sun, which we now know as sunspots? And people have actually continued observing these sunspots every day. And in 1844, Schwabe discovered that this sunspot has a cyclic or periodic nature. So from a solar maximum, that is the maximum sunspot cycle, to the minimum sunspot cycle is, and then to the next maximum, like that it goes. And the periodicity is about 11-year cycle, which we call as the solar cycle Now, since people were observing geomagnetic field also and the sunspots, people naturally observed that some disturbances in the geomagnetic field of Earth occur, and these disturbances of the events are connected with the sunspot cycle. So, like when the sunspot cycle maximizes, you see more geomagnetic disturbances also. Like wise there was a statistical understanding or observation, and then happened the Carrington event. Richard Carrington, a scientist he was observing sun very meticulously and make this kind of sketches of sunspots every day. So it was 1st September 1859 around 11:20 local time. He saw that two patches of very intense bright white light broke out in the positions A and B marked in this picture, that is near a sunspot region. And then he saw that it was so bright a flash. So he just reported that, and then around 17 hours later, there was a great geomagnetic disturbance which actually disrupted a lot of telegraph services that day. So people naturally thought that this could be a sun-earth connection. So whatever unusual episode Carrington has observed could be having some bearing on what has happened in the geomagnetic field and telegraph service center. So there was a discussion that it could be sun-earth connection, but some people even then told that this could be mere coincidence. Then came a very seminal discovery, or a very profound discovery which really changed everything. That is, in 1908, Hale discovered that sun is a magnetic star. He wrote a report he reported that on the probable existence of a magnetic field in sunspots. So he identified that these dark spots which we see in the sun, on the sun, are really connected to the magnetic nature of the sun. And basically, sunspots are the manifestations of the solar magnetic field. Now, this is such an important discovery that even the substantial fraction of even today's work in solar physics and space weather, including all our observations, many of our observations and modeling, are devoted to understanding these enigmatic magnetic field variations in the sun. In this picture, what you are seeing here is a sunspot, which is in the visible light. These dark spots which you are seeing are the sunspot. And then in the right, what you are seeing is a magnetogram measured by a spacecraft. So wherever you see a sunspot, you can see the magnetic field, positive and negative polarity fields, which are related to the sunspot. So sunspots are basically manifestations of our solar magnetic field. Now, if as sunspot is a manifestation of a solar magnetic field, then obviously the sunspot cycle is actually a solar magnetic dynamo cycle. This people have understood. And then in the 1930s, Bertels, what he has seen is that during solar minimum also, he found a lot of geomagnetic storms occur. And when he closely analyzed the data, he understood that these storms have a 27-day periodicity, which is same as the solar rotation period. Now we understand them as co-rotating interaction region, which is a cause of major space weather event during low solar activity. These co-rotating interaction regions are high-speed streams originating from the coronal holes of the sun. So by these kind of studies, we have established that there is a definite connection between what is happening in the sun and then what is happening at the Earth or Earth's geomagnetic field. So the connection is that both have their own magnetic fields, and probably the interaction is what is causing space weather impact. Now, with that understanding, let us see the driver of planetary space weather, that is the sun. When we mask the solar disk during an eclipse, naturally, we can see its atmosphere, outermost solar atmosphere, that is called corona, which is a fully ionized plasma with magnetic field that is millions of degrees hot. So this region, which is a fully ionized magnetic plasma, can emit extreme ultraviolet light. For example, the ionized helium can emit at 30.4 nanometer. To compare, visible light is around 400 to 700 nanometer, as you know. So once this UV light is emitted, these can actually affect our planetary atmospheres. That's what we will be seeing now. So before that, not only UV radiation, sun emits in the other wavelengths also, and this picture shows a solar spectrum. Average value of the spectral irradiance plotted in the y-axis and wavelength in the x-axis. So you can see X from XUV to IR, and this actually matches with a Planck's black body model with an effective temperature of 5,800 Kelvin. And we can see in the bottom axis the relative variability, how much it varies over a solar cycle. So you can see that the axis goes from 10 raised to -2 to around 100. And then we can see that visible or IR have very little change over an 11-year cycle, which we also know. We don't notice a substantial change in visible or IR radiation because a sunspot maximum or sunspot minimum time. But when we see the extreme ultraviolet or the X-ray radiation, etc., it has around 100% or more variability from when you compare a sunspot maximum to a sunspot minimum. Now, with this understanding, let us see how it arrives the Earth and other planets and what the planets have to offer to this incoming radiation. So we know that these are the planets and these have atmospheres with different composition. As you can see, Venus and Mars have a carbon dioxide dominated atmosphere and Earth has a nitrogen dominated atmosphere. As you might have heard in the last lecture, the gas giants have hydrogen and hydrocarbon dominated atmospheres. And these and according to the sun planet distance, the solar radiation also arrives with longer times, takes longer time to arrive at farther planets. And this, not only these planets have atmospheres, some of them have magnetic field, intrinsic magnetic field too. For example, Earth has a dipole magnetic field, which Venus doesn't have. Mars has a very weak crustal magnetism associated with that, whereas all these gas giants have their dipolar magnetic fields. Now, with this kind of a background, when a solar radiation, the X-ray, extreme ultraviolet and soft X-ray reaches these planets, it does something very drastic. That is, this UV radiation can ionize the planetary upper atmosphere, creating an ionosphere of planet. This is a partially ionized plasma seen in every planet. Now, this picture shows an example of our own Earth's ionosphere, which starts from around 80 kilometer and goes to very high altitudes. Now, the lower altitudes are known as the D region, then E region, and the highest degree of plasma is seen at the F region. The F region stays even during the night side because of the longer lifetimes of recombination of these ions to again back to neutrals. And then we have the D and E regions mostly disappearing during the night. So this is basically the impact of solar radiation into a planet. Now, as I told, not only the radiation, sun emits particles or plasma and magnetic fields also, and this magnetic field is what we call as the interplanetary magnetic field, which is basically the solar magnetic field. And this is the typical velocity of solar wind measured by Ulysses satellite. The uniqueness of Ulysses satellite is that it went to out of the ecliptic plane even and measured the solar wind at different latitudes of the sun. And it found that the typical solar wind speed is around 400 kilometers, whereas the high-speed streams from the higher latitude regions can reach up to 700 to 800 kilometers. This is a non-eruption case. Now, this solar wind and the magnetic field associated with that also reaches several planets. So here is and as the sun-planet distance increases, the magnitude of the solar wind density as well as the IMF, that is interplanetary magnetic field magnitude, reduces. And the arrival time also increases as the sun-planet distance increases. So around 4 days, typical solar wind of 400 kilometers per second takes around 4 days to reach Earth. Now, with this background, we understand that it is the solar magnetic field which drives the solar storms. So let us have a closer look to the sun and the solar magnetic field. This is an ultraviolet image of the sun, which reveals the loops of hot ionized gas trapped in magnetic fields. So as the sun rotates and as the sun rotates with differential velocities, these kind of magnetic fields can get entangled, break apart, and when they break apart, they release magnetized plasma. These plasma, what you're seeing here, will be released, and this is the major cause of severe space weather. So what are all these solar magnetic eruptions can cause? The solar magnetic eruptions, as I told, is caused by the sudden magnetic reconnection in the solar outer atmosphere, where this magnetic fields can get entangled and break apart. And then this happens in the chromosphere or corona and corona, and which can be seen as flares, associated electromagnetic radiation with the explosion. This can emit from radio waves to even gamma rays. And then the plasma cloud, which is erupted, can also reach planets with giant clouds of magnetic plasma. Then we call them as coronal mass ejections, with maximum speeds can even exceed 1,000 kilometers per second. And that is why the Carrington storm reached the Earth within around 16-17 hours. Apart from this, highly energetic particles can also be emitted or accelerated during these eruption events that we call as SCPs, which are a concern to the satellite electronics. So let us see how a coronal mass ejection looks like. This is a typical coronal mass ejection, which carries actually billions of tons of coronal material and embedded magnetic field. And so this it can be even slower than around 300 kilometers also sometimes, and the fastest can be around 2,000 kilometers per second, as I told, and which can reach our planet within hours. But solar flares, which are actually the brightening of a region of sun, typically lasting several minutes. And as we know, the solar radiation, because it is electromagnetic radiation, as I told earlier, it can reach our planet within 8 minutes. Earth case, and then this can actually give out a lot of energy in a short time. So the solar flares are visible in white light as Carrington observed, but they are very often readily noticed in the bright X-ray and ultraviolet emissions. What we see here is an ultraviolet image of the sun in a November 2003, which was a very intense storm. So what happens when a solar storm hits? As I told, Earth is a giant magnet. So assume that Earth has a bar magnet placed inside that. Then it should be, if you trace those magnetic field lines in space, it should look like this, a very symmetric dipolar magnetic structure. But in reality, this doesn't look like that. The solar wind makes the Earth's dipole magnetic field into a different structure. The day side is getting compressed and the night side is getting stretched. This structure we call as the magnetosphere. And one more interesting point to note here is that at very low altitudes near the surface, the dipole structure is preserved. And because of that, the solar wind is not entering directly into these regions. So the magnetosphere actually shields the Earth from the direct entry of solar wind particles. Now, sometimes when a solar storm occurs, sometimes means when a solar storm occurs, this doesn't happen. What happens is when the direction of the solar wind field, magnetic field becomes exactly opposite to that of the Earth. And here what we can see is because it comes at two opposite polarities, this gets cancelled. And then there is a opening of the magnetic configuration through which the particles can really go inside. So for a short time, this magnetic flipping or the magnetic field, the solar wind magnetic field becoming southward, opens up a gateway for particles to enter into the Earth's magnetosphere. And the amount of energy released by this process can be formidable. And this process is called magnetic reconnection. Now, once the plasma sees a magnetic field line, it starts following these field lines, and the particles can eventually reach the upper atmosphere of planets. Now, before going into that, let's sphere away, and that is one of the major mechanisms for atmospheric escape of a planet like Mars. Now, going into the impacts, again we will take Earth as an example. The solar flare impact, actually what happens when a flare hits, the X-ray and ultraviolet radiations increase by orders of magnitude during large flare events. So ionization also can suddenly increase. And when there is a sudden increase in the ionosphere down to the D region, the radio waves can be absorbed. This impact radio communication, or this can disrupt radio communication. For example, if you are using an HF radio for communication, then this can be disrupted. And then, as I told, the giant magnetic cloud, if it comes and hits the Earth, there commences a geomagnetic storm. And in the 1990s itself, we have understood that the magnetic reconnection is a process by which the geomagnetic storms occur, or the solar wind really connects with the Earth's magnetic field. So, as I told, when the storm comes towards us, the reconnection occurs, and then these particles find their way to the Earth's upper atmosphere. And then these particles also causes enhanced ionization and excitation, and then this excitation can emit lights of varying color and complexity. So this is what we observe as aurora with different colors, that is green, red, etc., and also in the other wavelengths also. And following the impact of a CME, because a lot of charged particles come, the intensity and the extent of the aurora increases. And just a point note here, this auroral oval, where most of the particle precipitation occurs because of the field line geometry, is not centered at the geographic pole, but at the geomagnetic pole of the planet. So I just want you to think about how aurora will look like in Mars, because in Earth we have the field lines to protect us in the Earth's equatorial and low latitude region, whereas Mars doesn't have a global magnetic field. So just think about it, how aurora will look like in Mars, and you will see a lot of images of Mars with what kind of aurora you will be seeing if you just Google. I'm not going to show it, just yeah, I just want you to think about it and find it out. So just let us go into the physics of geomagnetic storms. Basic understanding what we have with our electrodynamics is about a changing magnetic field generates an electric field. So that's Faraday's law, Maxwell-Faraday's law, del cross E is equal to minus dou B by dou T, where this is the partial time derivative, and this is the electric field which is generated. Now, as we saw, the solar wind, when it interacts with the Earth's magnetic field, our Earth's magnetic field changes. And then we have, so then that means there should be an electric field which is generated. Now, Ohm's law says that this electric field in a conductor can create an electric current. J is equal to sigma E, where sigma is the conductivity. And if you have a moving plasma in a magnetic field, that also creates a current which is U cross B. So there is a current which is generated in a conductor. So what are the conductors in the case of space weather? That is, one is planetary atmospheres. Another one, Earth's lithosphere or surface is also a good conductor, which can actually cause what we call as geomagnetically induced currents. This has huge impact in terms of space weather, especially in the high latitudes where your conductivity enhances significantly by the particle entry into the upper atmosphere. For example, on 13th March 1989, the Canada had a power grid which crashed because of a space weather event, and 6 million people lost electricity for as long as 9 hours. And later on, we understand that this was caused by a space weather event. So this is a technological impact even at the ground level. Going into the LEO orbit, low Earth orbit, we already know that J is equal to sigma E plus U cross B, where you have a plasma which is moving with the velocity U, and we have the magnetic field, and the changing magnetic field has generated an electric field. So electric currents are now generated in the ionosphere, which is enhanced during a storm time. And then this ionospheric currents can heat and expand the thermosphere. The thermosphere is the neutral counterpart of the upper atmosphere. As I told, the ionosphere is not a fully ionized plasma, it is only a partially ionized plasma. So it can actually expand, the currents can heat and expand the thermosphere, and then the expanded thermosphere can cause an increased drag on satellites at low Earth orbit. So increased drag can change your satellite orbits. This is very important as the number of satellites in the LEO has doubled due to these mega constellations like Starlink, OneWeb, etc. So now with this understanding on space weather, can we really see what happened to those 38 satellites in February 2022? What happened is as follows. On January 29, 2022, the sun gave out a very moderate flare and a related coronal mass ejection. And this material reached the sun. From the sun, it reached in a few days at Earth. Now, on February 3, the Starlink launched satellites to a parking orbit of around 210 kilometers, which has sufficient amount of density in the thermosphere. So this thermosphere, due to the presence of these currents in the currents due to storm, the thermosphere had heated up, then enhanced the drag, and this enhancement of the drag was around 50%. And this actually prevented the satellite orbit-rising maneuvers, and eventually the satellites were re-entered to the Earth's atmosphere and lost. Actually, the important factor is that though we have observations of the sun and the flare, etc., no forecasting model could predict this 50% of enhanced drag, or this much a moderate flare could cause this much havoc at these altitudes. So this is how the 38 satellites were lost, which was really an alarming sign of how important space weather is. And also, solar energetic particles can penetrate satellite electronics, as I told, can cause failures during space weather events. So to summarize, understanding and forecasting space weather is essential for safeguarding our technology and enabling safe space exploration to Earth and to other planets. For that, We need observations of the sun and planetary ionospheres, magnetospheres, etc., and model simulations to calculate parameters like drag, etc. So the solar observations are provided by several satellites like ACE, WIND, SOHO, our own Aditya L1. These are at the L1 points, and Parker Solar Probe, Solar Orbiter kind of satellites go very closer to the sun and observe them. And we have several satellites to study, observe planetary ionospheres and magnetospheres as well. So with this, I conclude. Thank you.